we were in the midst of a proof of a theorem characterizing the open sets in the real line, right. We wanted to prove that every open set in the real line can be expressed as a union of a countable family of pairwise disjoint open intervals, right. So let us start, and we had also started proof, we had taken some steps, so let us begin with that. Suppose G is open in R, okay. Then we had defined one relation on points in G. So suppose we say, suppose we take x y in G, then we had said that x is related to y. This means there exists an open interval I, such that these 2 points belong to that open interval, x and y lie in that interval, and this I is contained in G, okay, right. And we have already seen that this defines an equivalence relation, okay, this defines an equivalence relation on the set of all points in G, and we already know that every equivalence relation brings about what is called a partition of G, okay, that is a union, G can be a union of all equivalence classes of elements in G. So suppose we denote by this symbol equivalence class containing X, okay, so this is an equivalence relation, okay, this is an equivalence relation. Okay, then so this X placed in the square bracket, that denotes equivalence class containing X. Then what we already know is that G is nothing but union of all these equivalence classes, okay, okay. And what we also know is that if we take any 2 equivalence classes in this family, then they are either disjoint or they simply coincide, okay, right. There is so this is a disjoint union, okay, alright. So what remains to be shown is the following: we should show that each of this is an open interval, each of this equivalence class is an open interval, and it is a countable family, okay, it is a countable family, okay. Let us first show that it is an interval, okay, let us, or okay, I mean the same proof will more or less show that it is an open interval. Now how does one show that something is an interval? We have seen that yesterday, that is interval is nothing but you assume that there are 2 points in the set, okay, then all the points lying in between those 2 should also lie in the set, okay. So the first to show that this equivalence class is an interval, let us say this is what we want to show first, this is an interval, okay. So now so suppose alpha beta belong to this equivalence class, okay, suppose alpha beta belong to this equivalence class and alpha is strictly less than beta, okay. Then what we need to show is that any point lying between alpha and beta is also in that same equivalence class, right, okay, okay. But alpha and beta are in the same equivalence class, it means that alpha and beta are related by this relation, that is clear, because both are related to X and it is an equivalence relation, okay. So this particular thing implies that alpha is related to beta, okay, alright, and that means that there exists an open interval, okay, that means that there exists an open interval which contains both of these points and which is contained in G, okay. So this means there exists an open interval okay, such that alpha and beta both belong to I and I is contained in G, okay, okay. So does it immediately say that if alpha and beta belongs to I, and this is an interval, okay, and so all the points lying between alpha and beta also must lie, this, so this, since I is an interval, we can say that since I is an interval, we know that this closed interval alpha to beta that is contained in I, okay. Okay. We can say, but what we want is that this whole thing is inside this equivalence class containing X, okay. Now to do that, what we need to show that if you take any point in this closed interval, so suppose you take any gamma lying between alpha and beta, okay, then okay, that is to show that, let us consider that, okay, suppose alpha less than gamma less than beta, okay. Of course we can take less than or equal to also, but as far as alpha and beta are concerned, they are already in that, okay, okay, okay. But is it clear that gamma is related to alpha? We can take the same interval I, okay, we can take the same, because that is how our equivalence relation. So it so this implies that gamma is related to alpha, okay, and alpha is in this equivalence class, so that means gamma is related to X also, okay. So this means gamma is related to X also, or which is same as saying that gamma belongs to the equivalence class X, okay, okay. That shows that shows that this is an interval, okay, that shows that this is an interval, right, okay, alright. Now how does it show that it is an open interval? Well, you can say that if you take any point, in fact the same proof, for example if you take any alpha in this, okay, we already know that there exists an open interval which contains that point, and which is now we have shown that open interval, the open interval which contains in G, so which is contained in G, so it also shows that this is not only an interval but it is an open interval, okay, alright, okay. So each of this, let me just write this conclusion, so each of this equivalence class is an open interval, for every X in G, okay. So what have we proved till now? That each of this is an open interval. We already know that it's a, so G can be written as a disjoint union of open intervals, of a family of open intervals, okay, okay. Now what is left? We have to show that show that this is a countable family. We have to show this is a countable family, okay. Now this is where we use property of the real numbers, okay, right. Is it correct to say that every open interval will contain at least one rational point, right? Every open interval will contain at least one rational point, okay. Suppose you take two disjoint intervals, okay, then they have to contain different rational numbers, it cannot be the same, okay. So what you can do is that from each of these intervals you pick up one rational number, okay, from each of this interval you pick up one rational numbers, okay. So that will be some subset of rational numbers, okay, that has to be a countable set, because we have already shown that set of our rational numbers is countable, right, okay. And hence so, and the cardinality of that, okay, should be same as the cardinality of this family, because we have picked up exactly one number from one rational number from each of this interval, okay, right. So this has to be a countable set, okay, this has to be a countable family, rather this has to be a countable family, is it clear, okay. And it will also be clear that this argument will not work in some other metric space, okay, it works in this metric space because you have this set of all rational numbers which has this property that every interval contains, every open interval will contain at least one rational number, okay. That is why we can, that is why from whatever family is there we can show that it is a countable family, is it clear, okay. So that completes the proof of that theorem, okay. Then we are more or less close to finishing the discussion on open sets, but there are only one or two small points which let me discuss. See, there is one terminology which you come across very often, which is called neighborhood, okay. It can be neighborhood of a set or a neighborhood of a point, okay. Suppose we take, say, let us say XD is a metric space, and suppose we take two sets A and B, and such that A is contained in B. These both are subsets of X and A is contained in B. Okay. Then we want to say what is meant by saying that B is a neighborhood of A. Okay. Okay. We want to say what is meant by saying that B is a neighborhood of A. Okay. There is a slightly non-uniform practice in this terminology. Okay. First, let me say what is how it is defined in Simmons. Okay. Okay. B is said to be a neighborhood of A if B contains an open set which contains A. Okay. So let us take that definition first. Okay. So B is said to be a neighborhood. Okay, this is a standard short form for neighborhood. Okay, NBHD. Okay, this is standard short form. Okay. B is said to be a neighborhood of A if B should contain an open set and that open set should contain A. Okay, right. So if there exists an open set G such that A is contained in G and G is contained in B. Okay. Of course, we have not said that B itself should be open. Okay. If in particular B is open, then that is fine. Okay. You can take that set G as B itself. Okay. Right. So in Rudin, the definition is as follows: that B is called a neighborhood of A if B is open. Okay. If B is open and B contains A, it is called a neighborhood of A. Okay. So what Simmons would call open neighborhood. Okay. What Simmons would call open neighborhood. So that is a slight difference there. It should be clear to you that if B is a neighborhood of A, it also means that A is contained in interior of B. Okay. It means A is contained in the interior of B, and that will take care of both the things. Okay. And in particular, A can be just a single point. Okay. If A is a singleton set, we say that is a neighborhood of a point. Okay. Right. And neighborhood of a point, you can see that since this G has to be an open set and this is just a single point, then a neighborhood of a point will always contain an open ball centered at that point. Okay. Then there is one more thing that we want to discuss, and that is the following. Again, suppose we start with a metric space XD. Okay. And suppose we take a subset Y of X. Okay. Suppose we take a subset Y of X. Okay. Then we also know that this Y itself is also a metric space. Okay. Given by the induced metric which we can denote by D suffix Y, right. Okay. Now our question is as follows: suppose I take a subset which is in Y. Suppose A is a subset of Y, and anyway Y is a subset of X. Okay. Then A, whether, for example, we want to ask whether A is open or not. Okay. Whether A is open or not, but this will have two meanings. Okay. A is open regarded as a subset of X, or A is open regarded as a subset of Y. Okay. In general, these two things are different. Okay. For example, Y itself may not be an open set. Okay. Okay. But Y regarded as a subset of Y itself will always be open. Okay. Because we have seen that the full metric space is always an open set. So if we are taking Y itself as a metric space, then in that metric space Y is open, right. So Y is open in Y, Y may or may not be open in X. So let us ask a question in general. Suppose we take a subset of Y. Okay. What is the relationship between saying that A is open in Y and A is open in, or in general we can say that when can we say that A regarded as Y, a subset A of Y is open in Y. Okay. To do that, best thing to do is look at the relationship between the two different open balls. Okay. So suppose I take any point, let us say A is a point in Y. Okay. So and let us say take R bigger than 0, okay. R bigger than 0. Okay. Then we want to talk of, let us say, open ball with center at A and radius R. Okay. Open, let us say, open ball with center at A and radius R. Okay. Alright. But now you will see that this will have two different meanings. Okay. Whether you regard that as an open ball in Y or an open ball in X, right. okay, because what will be the meaning of saying that this open ball regarded as a open ball in X? By definition this will be set of all x in X and with the property that d a x is strictly less than R, okay. So to distinguish between these two things, suppose I denote this by u suffix x, okay, just to denote that we are now talking of open ball in X, okay. So similarly suppose I take u suffix y of AR, what will be that? Now you cannot take all points in X because you are only in this metric space Y, okay, you are only in the metric space Y, okay. So you take only those points in which lie in Y. Among all these, out of all these points you take only those points which lie in Y, okay. So that is the set of all y in Y such that d a y is less than R, okay. Okay. Now how are these two sets related? Can you say something more than that? That is clear, uy is contained in ux is fine. Can you give even better description? That's right, that is, this is nothing but the intersection of this with y, right. What we can say is that this open ball u suffix y AR is nothing but u suffix x AR intersection y. That is clear, okay, alright. Now using this you can show the following, okay. Let me write this as a theorem, okay. A is open in Y, okay, we are having this setup, okay. A is contained in Y, Y is contained in X, okay. A is open in Y if and only if there exists an open set G in X, there exists an open set G in X such that A is equal to G intersection Y. Okay, right. So this answers the questions completely. When is A open in Y? Okay, if you can find some open set G in X, okay, such and if you can write A as Y intersection G, then A is open in Y. Proof is fairly simple and I shall leave it to you as an exercise, okay. I will not discuss it here. In fact this part is trivial, right, okay. If you take G is an open set in X and G and Y both are open, so their intersection is open, so that is fine, okay, right. Similarly the other way, okay, if A is open in Y you have to find open set G such that this happens, but for that you use this, okay, for that you use this fact, okay. Okay. Now let us also go back to certain types of points which we have discussed, okay. Till now let us say given a metric space X and a subset A of X, okay, we have discussed what is meant by interior point, okay, we have also discussed what is meant by an exterior point and boundary point, okay. Let us now take a few more types of points, okay. So suppose X is a point, okay, X may or may not belong to A, okay. So now what I want to define is what is called a closure point, okay. X belongs to X is said to be a closure point of A, okay, closure point of A if what happens is the following, okay. If you take any open ball with center at X, its intersection with A should be non-empty, okay, right, its intersection with A should be non, so that means every open ball containing x should have a non-empty intersection with A. Okay. So if for every r bigger than 0 u x r intersection A is non-empty. That means every open ball with center at x contains a point from A. Okay. If that happens, it is called a closure point. Okay. Obviously, if the point x is in A, it will always be a closure point. Okay. It will always be a closure point. Okay. All right. So, and the set of all such closure points is called a closure of A. Okay. So, and we shall denote that by A. This it is called closure of A. That is the set of all closure points of A. Okay. And the standard notation for that is A closure. Okay. That is A with some bar. Okay. A closure, or some books also write this CL of A closure. Okay. And what we have seen just now is that every point of A is a closure point of A. In other words, it is this A is contained in A closure always. Okay. A is contained in A closure always. Okay. All right. Okay. Now there is another concept which is very closely related to this, called closure point. It is called limit point. Okay. Let me just write it here because there is a small change here. Limit point. Okay. For the limit point, what we want is that this intersection u x r intersection, just non-empty is not sufficient. It should contain some point which is different from this point x. Okay. Then it is called a limit point. Okay. Right. That is, if you if every neighborhood of if every open set or every open ball containing x contains a point from A different from the point x, that is called a limit point. Okay. So we can say that for limit point, if u x r intersection, let me write this A minus this singleton x. Okay. A minus singleton x, right. That is, remove the, if x does not belong to A minus singleton x will be just A. Okay. Right. So u x r intersection, this should be non-empty. Right. So if x is a closure point of A, but if x is not in A, then it has to be a limit point, right. Okay. Right. But only thing is that if x is inside A, then it can be a closure point without being a limit point. Okay. Without being a limit point. Okay. All right. See, just as we have said A closure is the set of all closure points of A, similarly the set of all limit points, that is also has a special name. It is called the derived set of A. Okay. It is denoted as A prime. A prime, the derived set of A, called the derived set of A. And this is nothing but the set of all limit points of A. And from whatever we have discussed just now, we already know that A is contained in A closure. Okay. What about this? Can we also say that this A prime is also contained in A closure? Okay. Right. Just now, because every limit point is obviously a closure point. Only converse may not be true, right? Okay. And if a point is in okay, suppose a point is not a limit point, but it is, if it is still in the closure, then it must be the point of A, right? Because we have seen that if a point is a closure point, and if it is not in A, then it has to be a limit point, it has to be, okay. In other words, if you summarize all this discussion, what it means is this, that is A closure is nothing but A union A prime, right. That is A union the derived set, that is A along with all its limit points, that forms what is called the closure of A, okay, alright. Now let us also see what is meant by saying that something is not a closure point or something is not a limit point, okay, alright. Let us just take the definition once again. See, suppose X is not a closure point, okay, what does it mean? It means that this is not true, okay, for every R what we are saying is not true. That means what? That means there exists some R, that means there exists some R such that this intersection is empty, right, okay. So let us just see what it means, okay, alright. So suppose X is not a closure point, which means what? Suppose X belongs to X minus A closure, okay, right. So what does it mean? It means that there exists some R, okay, it means that there exists R bigger than 0 such that open ball with center at X and radius R intersection A is empty, okay, open ball with center at A, okay, alright. Now this thing, open ball with center at X and radius R intersection A is empty, is it same as saying that U X R is contained in X minus A, right? Its intersection with A is empty means it is contained in its complement, right. So these two things are equivalent, okay, okay, I will say. So in fact here also I can say these two things are equivalent, okay. X is not in A closure is exactly same as saying that there exists some R such that U X R intersection A is empty, okay. But what is the meaning of this, that there exists some R such that open ball with center at X and radius R is inside X minus A means it is an interior point of X minus A, right, it is an interior point of X minus A, or which is same as what we have called it is an exterior point of A, okay. So if something is not in the closure of A, then it has to be an exterior point of A. So in other words, suppose I want to write all these arguments in the symbol, what we have proved is this, that is X minus A closure or A closure complement is same as interior of X minus A, or which is what we have called exterior of A, exterior of A, okay. Alright, okay. Now let us also say similar thing about what is meant by saying that something is not a limit point, okay. So suppose X is not a limit point of A, okay, let us say. Is this clear whatever we have done, okay? X is not in the closure means it is in the exterior, okay, and so it means complement of A closure is same as the exterior of A, alright. Next is suppose X is not a limit point of A, X is not limit point of A. It means what? Again only thing is that you will mean that this intersection of X with R, sorry U X R intersection A, intersection this A minus A, okay, that is empty, okay, that is it means U X R intersection A, this contains no point of A other than X itself, okay, other than X itself, okay. So this is same as saying that U X R intersection this A minus singleton X is empty, okay, and that means what, that is this open ball with center at X and radius R, if at all it has to contain any point from A, then that point must be X itself, okay, and that can happen if X itself is a point of A, okay, that can happen if X itself is a point of A, okay. In other words, suppose X is a point of A, suppose X lies in A, okay, and X is not a limit point, okay, x lies in A and x is not a limit point. That means what should happen? There should exist some neighborhood, that is there should exist some open ball such that containing x, such that that open ball contains no other points of A, okay, only that point itself, okay, right. If such a thing happens, such a point is called an isolated point, okay. So such an x, that is, suppose if x belongs to A and x is not a limit point of A, then x is called an isolated point of A, that is, let us say if x, that is if x belongs to A and if it is not a limit point, that is if x belongs to A minus A prime, okay, then x is called an isolated point. Okay. Alright. So what are the definitions that we have seen? Closure point, limit point and isolated point, okay, and if something is not a closure point, then it is a exterior point, and if something is not a limit point and if it is a point of A, then it is an isolated point, okay. Alright. I think it is better we shall take some example. Let us take an example from R, okay. So suppose I take R is this matrix, usual matrix space. So suppose A is this set, okay, say 1, 1 by 2, 1 by 3, etc., in general 1 by n, okay, and suppose I will add 0 also to it. Okay. Okay. Now each of these points are in obviously each of these are in the closure, okay, each of these points are in the closure, okay. Is there any other point outside this which is in the closure? Yeah, so 0 is in the closure, but and suppose you take any point other than this, okay, then for example let us say I take a point 2, okay, point 2 is none of this, but it is also not in the closure, because I can take, if you take let us say R as half, okay, then open interval with center at 2 and radius half, its intersection with A will be empty, okay. So in fact this A is same as A closure, okay, no point outside A is in the closure of A, okay, alright. Now out of all these points 1 etc., which are limit points? This is the only point which is limit, because 0 is a point which has this property that if you take any interval containing 0, it will contain at least one of these, in fact it will contain infinitely many, but at least one of these points other than 0 itself, okay. So 0 is a limit point, okay, right. So the derived set here A prime is singleton 0, okay, and all these other points 1 by 2 etc., all of these are isolated points, right. Is it clear that if you take any, for example if you take say 1 by 4, okay, then you can easily find an open R such that interval with center at 1 by 4 and R radius R will not contain any other point from here, okay, it is very easy to construct, right, okay, and we can do it for any n, okay. So all these are isolated points, okay. There is one more thing that we should relate to this concept of closure, and that is the following, okay. We have already defined what is meant by distance between x and A, okay, we already defined what is meant by distance between x and A, okay. So what I want to say next is x belongs to A closure, x belongs to A closure if and only distance between x and A is equal to 0. Okay. Can you see this? Okay. Let us see how this can be proved. Okay. Suppose x belongs to A closure. Okay. Suppose x belongs to A closure. Then what you know is that for every R, for every r open ball with center at x and radius r intersection A is non-empty, which means that distance between x and A is less than or equal to r, that is suppose x belongs to A closure, that implies distance between x and A is less than or equal to r for every r bigger than 0, right, okay, for every r bigger than 0, okay. But if it is less than or equal to r for every r bigger than 0, then it has to be only, and this is anyway a non-zero number, anyway a non-negative number, so this will if it is less than or equal to every positive number, then it has to be 0, right, okay. So x belongs to A closure implies distance between x and A is 0, okay. On the other hand, suppose distance between x and A is 0, okay, then look at the definition. How did we define distance between x? It is infimum of distance between x and A, where infimum is taken over all A in A, okay, alright. And from the definition of infimum, you will see that if you take any strictly positive r, then that is not a lower bound because 0 is an infimum. So there should exist some A such that distance between x and A is less than r, okay, which is same as saying that intersection of u x r with A should be non-empty, right, okay. So try to write this proof on your own, okay, but this is a good characterization of the closure, okay, that is to decide whether a point belongs to a closure or not, it is equivalent to saying that its distance from the set A is 0, okay. Okay. Now having seen so many properties of the closure, now let us come to the important definition, okay, namely what is meant by a closed set, okay. So let us again say that XD is a metric space and A is contained in X. A is said to be closed in X if A coincides with A closure, okay, if A coincides with A closure, if A is equal to A closure. Okay. Of course, we know that A is always contained in A closure, okay, okay, right, that is this is always true, A is always contained in A closure, okay. So additional thing required is that these sets are the same, okay, which means what, which means every point in the, what is additional requirement is that this, that is A closure is contained in A, this is what is required, okay. That means every closure point should also be in A, okay, every closure point should also be a point of A, okay. Alright. Is it same as saying that A contains all its limit points, okay, because if a point is in A closure and if it is not in A, it has to be a limit point, so such a point should also be there in A, okay. So saying that A is a closed is same as saying that A contains all its closure points, that is same as saying that A contains all its limit points also, okay.
Basically all the boundary points are the limit point.
Yes,
all the boundary points are the limit point, because if we include the boundary in open set, it is a closed set.
yeah, okay,
Okay.
yeah, okay, we can say that, okay. So so that is how the closed sets are defined, and you can compare the definition with the open sets. In open sets what we had defined what is meant by an interior, and we had said that the set is open if A coincides with its interior, okay, and in the case of interior we know that interior of A is always contained in A, okay, it is the other way, okay, interior of A is always contained in A, okay, and when these two are equal we say that the set is open, okay. So which means that every point should be an interior point, okay. The definition of closure is the other way, A is always contained in A closure, and we will say that A is closed if every point in the closure is also a point of A, okay. And as somebody observed just now, it also means that A should contain its boundary, okay, because every point in the boundary is also in the closure, every point in the boundary is also in the closure, okay, okay. Now let us proceed further. we can now look at some examples of closed sets and some properties of the closed sets, but what we shall do is that instead of going to that, we shall prove one theorem which will immediately give you a big class of examples of closed sets, okay, right. So and that theorem is the following, okay. Let A be a subset of X, then A is closed if and only if its complement is open. Okay. A is closed if and only if its complement is open. Okay. Okay. Now I would say that the proof is more or less here already, okay. Here we have proved that X minus A closure is interior of X minus A, okay. Of course you have to observe here that is it clear to that interior of any set is an open set, okay. Interior of any set is an open set, that is elementary exercise that you can prove, okay. Now suppose A is a closed set, okay, that means A is equal to A closure, okay, that means A is equal to A closure. So that means X minus A closure is same as X minus A, okay, and if X minus A is same as interior of X minus A, X minus A must be open, right, okay, alright. Now on the other hand, suppose X minus A is open, okay, suppose X minus A is open, okay, then interior of X minus A should be same as X minus A, which means that X minus A closure is same as X minus A, right. And if X minus A closure is same as X minus A, using that you can prove that A is same as A closure, okay. So this X minus, so you can say the proof follows by just observing this X minus A closure is same as interior of X minus A, okay, okay. So this is a good characterization of closed sets. A set is closed if and only if its complement is open, okay. Now does it immediately give us a large number of examples of closed sets? All that you do is that whatever example of open sets we have seen, okay, take their complements, those are the examples of closed sets, okay. In addition to that, in order to justify our terminology, now we can say that why we had called certain balls as closed balls, okay. Just as after defining open set we proved that every open ball is an open set, in a similar way we shall now prove that every closed ball is a closed set, okay. So okay, every closed ball in a metric space is a closed set. Okay. Okay, now look at the proof. So we need to consider some closed ball, okay. So closed ball means what? We take some point A as the center and some positive number r. So closed ball is BAR, okay. This is nothing but a set of all x in X with the property that distance between A and X is less than or equal to r, okay. Okay. And using this we can say that to show that this is closed, we can show that its complement is open, okay. Okay, we will show that X minus this is open, okay, right. We shall show X minus BAR is open. Okay. Once you understand this, okay, what is to be done after this is clear, okay, right. So in fact in this case certain diagram may help, okay. So suppose this is BAR, this is A and this is R, okay. What you need to show that X minus BAR is open, you need, suppose you take some point outside this, okay. So suppose I take some point y, then you should find some row such that open ball with center at y and radius rho is completely outside this. That is what we need to show, right. So let us say let y belong to this x minus b a r. What does that mean? It means distance between a and y must be strictly bigger, not greater or equal to, must be, it is closed ball, remember, okay. So distance between a and y must be strictly bigger than r, okay. So this implies distance between a and y is strictly bigger than r, okay. Now we do the same thing what we did in the last proof of similar type, okay. See, if this number is strictly bigger than r, I can always find some number rho such that it is bigger than r plus rho, okay, right. So let me continue here. Okay, choose rho bigger than 0 such that distance between a and y is bigger than r plus rho, okay. That is, this is the distance between a and y, so this is r, so choose rho such that if you add this r and rho, this distance should be still bigger than that, okay. So then what we need to show is that if you take this y and rho as the radius, then this open ball is completely outside this, okay. There is no common point between this open ball and this closed ball, okay, right. So then, okay, I will write this as a claim, that is open ball with center at y and radius rho is outside this, that is in this x minus b a r, okay. Okay, and to prove this we shall just use this, okay. Proof of this is very simple, just take some point here in this, okay. So suppose suppose I call that point z, let z belong to u y rho, okay. Then d z y is strictly less than rho, okay, dz y is strictly less than rho. Then what is it that we need to show? That dz a is strictly bigger than r, that is what we need to show, right. Does it follow from this? Okay, let us look at dza, let us look at dza, this is less than or equal to d z y plus d y a, okay. And using this it will follow that dza must be strictly bigger than r, right, dza must be strictly bigger than r, okay, right. So this is a closed set, so every closed ball is a closed set, is that clear? Okay. Then using the several properties of the open sets which we have discussed and using this particular theorem, we can prove several theorems about the closed sets, okay, right. For example, let me just write those theorems, okay. So let X D be a metric space, and since the proof is very straightforward, I will not spend much time in discussing this, okay. Then first thing is empty set and X are closed sets, and about unions and intersections the roles are interchanged here, okay. In case of open sets we know that the arbitrary union of open sets was open, here we can say that arbitrary intersection of closed sets is closed, okay. So if you take any family of closed sets, so suppose f alpha belonging to lambda is a family of closed sets, then intersection of this f alpha in lambda is closed. And when it comes to union of only finite family is closed. Okay, if f1 f2 fn are closed, if f1 f2 fn are closed, then union fj, j going from 1 to n is closed. In short, arbitrary intersection of closed sets are closed and finite union of closed sets is closed. It is completely opposite to what happens in case of open sets, and in the proof also you can prove that by using the corresponding property of open sets. For example, if since we know that phi is open, okay, so that means X is closed, okay, and similarly phi and X, since X is open, it means phi is closed, right, and you can do the same thing here. For example, if each f alpha is closed, it means its complement is open, okay, right. So you take the union of those complements, that will be nothing but the complement of this, okay, that will be open, so this is closed, and in a similar way you can prove this. In other words, you prove all these things using this theorem and the corresponding properties of open sets and the so called De Morgan's laws, okay, right. I think we will stop with that for today.